Now comes the answer to the very important question of how do I export the data from these raw capture files, these what are they? The magnetic flux transitions that are captured by the logic analyzer with the very strange music in the background. And how do we turn this into data? It's a very, very, very long process. But very simply, we're going to start with how we turn this into something that a computer program can read and process. And that's fairly simple. We've already gone to Options, Save Session, Settings, and Data. And so if you've been viewing any of my .logic data files and opening them with the Saley Logic Analyzer version 1.1.15, that's how I've been saving those. But the way I turn it into data, step one is I export the data. Now, it's important to understand what this does, because it certainly doesn't turn it into the binary files that I eventually add up with. There's hundreds, if not thousands, of lines of code that I've written between this step and the final binary files, with lots of error correction and so on and so forth. But the step starts here with export. So from this, I simply choose which channels to export, and I'm always choosing channel 0, which I've labeled 26 read data pulse. And the reason I've labeled it that is because it's pin 26 on the QIC 36 hardware interface for the QIC hard drive that I'm using. And as I think I've shown in another video, the only signal that I'm capturing using the logic analyzer is a single one, which is this pin 26, read data pulse, and I'm using channel 0 on the logic analyzer. So that's it. Samples to export, make sure I choose all time. Export format, CSV, comma separated values. There's a couple of other options. There's binary and VCD. I can't say that any of those have been better for the way I've done this. They could be better for someone else's process. But for me, I'm going the old-fashioned CSV file. And so we go here and say, gee, where are we going to export this? And this is where we're going to export it. This happens to be track 0 going forward. And so I'm just going to use this as the name. So exporting all of track 0, because I captured all of track 0. Now this takes a while. This was a DC 600A tape, and so there's about 90 seconds of data that I've captured, or magnetic flux transitions, data pulses that I've captured from the beginning of the tape to the end of the tape. So we're going through the export process now. So we'll wait momentarily while that finishes, and then I'm going to give some final comments about what to and not to do with the CSV file, depending on if you dare. And now that the export is complete, let's have a look. Or more specifically, let's not have a look. As I go over here to the folder where I put the CSV file, we can see it right here. Here it is, 0F CSV. Now, I'm going to tell you what I'm not going to do. I am not going to open this in Excel. Why? It's almost 1.2 gigabytes. It is a huge file with, I don't even know how many lines, how many rows. It will crash Excel. It will hang. It will just do no good whatsoever. Now, you can, if you're more daring, by all means, open it in Excel, but I'm not going to. I tried that once, and it did, just completely hang on me. I had to reboot and all that. My programs read this as a flat text file. Do not even open it. But I am going to take a small cross-section of this and show you what we see in here, just so you have a good understanding of what that export is. And so here it is, a subset of that export file, which is much, much smaller, 282 kilobytes to be exact. And I just used an editor, a hexadecimal editor that doesn't have a problem, processing things. It just opens this as a flat file, and I just took a chunk out. And I actually took a very specific chunk out because I wanted to demonstrate what we see here. So really, it's just the time and whether the read data pulse is high or low. So just to get the graphic understanding here, now I particularly extracted this section of the file so that I could demonstrate the relationship between what you see in the numbers in the text file and what you see here graphically in the user interface of the Saley Logic Analyzer. So this is where I took a chunk out. There was a lot of stuff here. Basically, it starts with 0, the very first data pulse on here, all the way back here. So it starts with this, and the first pulse, so on and so forth. Now, I'm not interested in the first pulse, at least not for these purposes, because as I have, may or may not have demonstrated in another video, if not, I will, that everything we see before the first data block and everything we see before even the tape starts moving is noise. Absolute noise. The tape hardware creates noise, and when the tape is moving, there's more noise before there's structured data on the tape, or structured magnetic flux transition reversals on the tape. And so identifying those differences here is very important. What I've done here is I've used this marker, this flag, to mark where I've visually identified the first block to be. And the way that I've done that is I've just zoomed in, and by the way, this is all noise. This is noise. I think this is noise before I started the tape, and I think the rest of this is noise after I started the tape. So the noise increases once I start the tape, but it's still noise all the way up until we get to some structured data. This is not structured data here. You see little blips of things, but it's just noise. And I don't know how else to explain it other than that. I wish I knew how to clean it up just for demonstration purposes, but there's ways to make sure that it doesn't get in the way. And besides, the original hardware has to deal with that noise anyway, because it's there, so it must know how to process it. It must. Anyway, my programs know how to process it too. So, even though the noise seems to get more dense here, this is still just noise. These flux transitions, data pulses, are just too far apart. I don't know what created them. But all of a sudden, right here, we have structured data. And we now can clearly see, all of a sudden, we have an organized preamble. Okay? Now, where I was going to go with that, before I go too deep into this, is just to show the basic relationship here. What I've done is I've picked... Oh, what did I pick? I have picked a section of flux transitions, a few before this point in here, just to demonstrate. So I captured just a little bit of the noise before this first pulse of what looks like the preamble. So I'm going to find that in here just for demonstration purposes. So I'm going to zoom in here, and I'm going to see that the number that I should see this change from 0 to 1, the exact time should be 0.585447 something, just before 0.585448, right? So 0.585447, because this is after the 9. So I'm going to look for that. Just a little search here. 0.5854479. And you can see I've searched for it here before. And here it is. Right there. It found it right away. This is exactly the time that I was expecting to see. And it gets even much more specific than that. But next to it is a 0, not a 1. So, when visually we see the line at the top, I guess that's a 1. And here, that's a 0. This is what I figured out. That the point at which it drops down, that's the 0. And the point at which it drops back or goes back up again, that's the 1. So this one right here, 0.858448375, comma 1, that should be this one. So let me zoom in just the right amount here. 0.858448 looks like 3 something. 0.8584483 and some change. 0.85844 0.858448375. That's the change, so to speak. All right, so what we've done is we found these two, both the down and the up of this, logic analyzer capture. But here's the important thing. I don't care what half of these things are. For example, I need to measure from this front edge here to this front edge here. I don't care how wide the pulse is. And as a matter of fact, the pulses should always be almost exactly the same width on the logic analyzer, because the data pulse is actually created by the hardware itself. It denotes a magnetic flux transition on the tape, or noise, but in this case the magnetic flux transition. And it's usually, very rarely any wider or narrower than this. And so the width is 0.4167 in this case. And so all of these are going to be close to that. This one's 0.3750. This one's 0.4167, 0.4167, so on and so forth. 3750. So, they're very, very close within range. As a matter of fact, they all seem to be snapping to a certain position. So, I'm not exactly sure. I'm capturing at 24 megahertz here. So I think it would find a width smaller than this. So I really think that that's just what the hardware is producing when it provides this data pulse. So since I'm measuring from the leading edge to the leading edge, this edge right here to this edge right here, and try to pay attention to my mouse instead of these arrows that show the measurements here, this edge right here to this edge right here, then what I'm doing is I just, my program ignores all of the ones. Anytime it finds one, it just ignores it. And my programs, all they do is they measure the time from this right here to the time from the previous zero. The time of this zero to the time of the previous zero. And therefore, the programs are measuring the distance from the leading edge to the leading edge. Now, I suppose it could be, the falling edge to the falling edge. The math, the concept should be the same. So you could do exactly the same thing just by capturing all of the ones and ignoring all of the zeros. I think it would work exactly the same way. Again, because these widths are just completely consistent. I know my programs were written on the 0 because that's what made sense to me at the time. So that's what we're going with. But this is the file. This is the the CSV file, and this is what it looks like. So if you were to open it in Notepad, or if you were to open it in Excel, you would see rows just like this, where this would be the first column and this would be the second column, and that would be it. Again, I'm not going to do that because I really think it would crash Excel at almost 1.2 gigabytes. But that's it. And so that's the first step of how I get the data out of this capture file, right? This logic data capture file of data pulses and magnetic flux transitions turned into data pulses captured by the logic analyzer. And so now the next thing would be to look at what my programs do when they measure this timing difference. And then we'll go from there. Thanks for watching, and we'll look forward to seeing you in the next video.